Let's consider multi-electron atoms. So, we've just solved the equations of motion for the electron and the hydrogen atom, and we got 4 quantum numbers. Now, let's look at, say, the helium atom and the rest of the atoms on the periodic table. Well, we run into a problem. The problem is we cannot solve the equations of motion for any atom except hydrogen. We might say there are over 100 known elements, and we can only solve one, a hydrogen atom. Well, that's true. The equations are just too complicated. We just don't have the mathematical tools to solve them. And so what do? We could just stop and study, some other discipline, or we can plow ahead. And what we do is we use the hydrogen atom as a model for all other atoms and elements. We're going to use the same quantum numbers that we got on hydrogen for all the other atoms. Now we have more than one electron. So say we have the helium atom. It has 2 electrons on it. So we use the same energy levels that we found on hydrogen and the orbitals. So we'll still have the 1s, the 2s, the 2p, 3d, and so forth. But we now have 2 electrons to accommodate. So where will those 2 electrons be? What possibilities can we have 2 electrons in these orbitals? How can they be accommodated? We need to satisfy something very important. It's called the Pauli exclusion principle. And that says that no 2 electrons can have all 4 quantum numbers the same. So, say we have our 1s orbital. I'm going to draw a line here, and I'm going to draw electrons as arrows. So, say I put an electron in the 1s orbital, and I'm going to use arrows so that the up arrow means the m sub s, the spin quantum number, is 1/2, and a down arrow means the m sub s quantum number is -1/2. So I'll just use that as a shorthand way of writing the quantum numbers. So say I have these 2 electrons, and I put them both in a 1s orbital on the helium atom. Let's look at the 4 quantum numbers. For the up arrow, n equals 1, l equals 0, m sub l equals 0, m sub s equals 1/2. The down arrow has the quantum numbers n equal 1, l equals 0, m sub l equals 0, m sub s equals -1/2. So 3 of the quantum numbers are the same, but here the 4th quantum number is different. So that follows the Pauli exclusion principle. That's allowed. However, if I had this, then all 4 quantum numbers would be the same, and this is not allowed, because the m sub s values would both be 1/2.